Let's continue on in our series about implementing unobservable preference heterogeneity into discrete choice models. Our last video introduced the concept of dynamic selection in a finite mixture model, and we left that video with a likelihood function that was going to be difficult to maximize because of the non-separability. And in today's video, we're going to talk about the EM algorithm, or expectation-maximization algorithm, and how it can be used in this type of a finite mixture model to dramatically simplify the estimation and restore additive separability to those different likelihood components. Reviewing from the previous video, we have our log likelihood function, which is non-separable because S is unobserved. So we need to first take the product of the likelihoods of each component of the model and then estimate the pi s's given the mixing distribution that we've assumed. And we're going to estimate alpha 2, alpha 1, and pi s together in the same estimation step. The paper that we're going to base the discussion of this video on was published in Econometrica in 2003, and it talks about how you can use the EM algorithm in a finite mixture model to restore additive separability of these likelihoods, and this opens the set of problems that can be estimated tractably, which is the big advantage to learning about and trying to implement this approach. So the authors of this paper are Peter Arcidiacono and John Jones, and Peter Arcidiacono was my dissertation advisor, and I definitely used a lot of these methods in my dissertation research. So the name of the game with the EM algorithm is that we want to restore additive separability to this finite mixture model. And as I mentioned before, EM stands for expectation maximization. And there's two steps to this, hence the E and the M. In the E step, we estimate the parameters of the mixing distribution, which in this case would be the pi s's. And then in the M step, we're going to pretend that we observe the true group that each unit in our sample belongs to. And then using that information, we're going to estimate the alphas sequentially, like we talked about in the prior video when we assumed that we could observe S. If you're familiar at all with machine learning, you might have come across the EM algorithm in that context. In machine learning, the EM algorithm is used as a way to fill in missing data or to identify clusters of similar groups in the data. But the EM algorithm is what's called an unsupervised learning algorithm in the machine learning literature. It's also sometimes called soft classification because the classification is based on unobserved attributes. If you've dealt with the naive Bayes classifier, then the naive Bayes classifier with unobservable classes would be estimated by the EM algorithm. It can also be contrasted with k-means clustering or other types of clustering, which are known as hard classifiers. So there's a lot of interdisciplinary application of the EM algorithm. And in this particular case, we're going to show how it can be brought into econometrics to resolve this dynamic selection problem that we introduced in a prior video. So in our case, the missing data, or the unobservable class that we're trying to predict, is the unobserved type that we're assuming is the source of our selection problem. So we have our non-separable log likelihood function like I showed you before, and under the conditions of the EM algorithm, we can write this non-separable likelihood function into a separable form, and all we do is we transform these pi's into q's, and then we can estimate L1 and L2 separately or in a sequential manner. The pi is the population probability that of any person in the population belonging to group S. The Q is the individual posterior probability that that particular unit belongs to that particular group. So I say posterior, then maybe if you've taken a Bayesian statistics class, or if you're familiar at all with Bayesian methods, you automatically are triggered by the word posterior. And that is because the EM algorithm is an application of Bayes' rule. But even if you're not familiar with Bayesian stuff, these Q's are basically the individual probability that unit I belongs to group S. And the Q's satisfy that they average up to the pi's. So these Q's are important because basically what happens is they turn into weights in the estimation of L1 and L2's likelihoods. And that's what restores the separability, is that we can think of Q times L2 as being a weighted maximum likelihood estimation, and then the same thing for L1. So the main twist is that we weight by the Q's, and then we can consistent estimates of all the parameters that we're interested in using this algorithm. So in stage 1 of the M step, we weight by the Q's the estimation of L of Y1, and then the same thing for L of Y2. And if the sequencing is opposite, then we do it in the correct sequencing order. And then in the E step, we effectively apply Bayes' rule to back out what the Q's are. And so we're looking at, well, what's the likelihood that I am of type S, given that I have to be one of the S's? And that's going to allow for the information across both of these likelihood components to inform us about what the class membership or the group membership is for unit I. So in this way, we do need the panel data to really tell us about the information that would lead us to conclude that unit I is definitely a member of group S and not of group S prime, for example. And then we just iterate on these E and M steps until the Q's converge. So we want to get that the Q's are not changing at all across iterations of the algorithm. Then we know we've converged, and then we have the consistent estimates that we are after. So what are some potential complications to this EM algorithm? Well, the first is that when we have this permanent unobserved heterogeneity, we no longer have global concavity of our likelihood functions. So this means that if we give it different starting values, we're going to get different estimates out of it. And so that's going to be a problem in terms of us finding the global maximum of the likelihood function as opposed to a local maximum. Another issue is standard errors. We're estimating things sequentially. And so the estimates of stage 1 of the M step are going to carry with them estimation error into our estimates of the second step. And if we don't correct this, then we're going to get misleading standard errors, because typically the estimation error from those two steps would be correlated in some way or have some covariance that we're ignoring by doing it sequentially. So the way to resolve this is to do bootstrapping. And basically the extent of these problems of local optima and estimation error in the parameters and the degree of covariance between the different stages, that's all problem specific. So you need to know your specific case, but basically the way that we resolve that is to do bootstrapping for the standard errors and to try lots of different starting values to make sure we've got a good coverage of the parameter space to make sure that we've got the global optimum that we're after. Thanks for joining this video about the EM algorithm. I hope you've learned something useful. I haven't gone through the code for how to do this. I might do that in another video later on, but it's not on my immediate agenda. But there are coding packages out there that you could use to assist you in applying this to your own econometric research if that's what you're doing and if that's why you're watching this video. Our next video will introduce a algorithm that is related to the EM algorithm called the MM algorithm. So I hope that you'll join me for that one as well.